In this video, we're going to continue analyzing a titration involving a strong acid and a weak base. Our titration would look something like this, where we would have our strong acid in our burette, and we would be adding certain volumes of the acid into a flask containing a solution of weak base. Our titration curve would look something like this, where we start out very basic, ultimately end up very acidic, and our equivalence point would be somewhere below neutral, below 7.0. So for a strong acid weak base titration, we must be able to calculate the pH of the solution at the following points. Before we start the titration, after we've started the titration, but before we've reached the equivalence point, at the equivalence point, and after or beyond the equivalence point. Each of these points along our titration curve involves a different strategy for calculating the pH. In this video, we're going to show you how to calculate the pH after we've passed the equivalence point. So our calculations would involve calculating the pH somewhere in this region down here, past the equivalence point. So calculating the pH for a strong acid weak base titration after the equivalence point involves the following steps. First, it's always good to check to be sure where you're at on the titration curve. Are you before the equivalence point, at, or beyond the equivalence point? Obviously, in this video, we told you we're going to calculate the pH beyond the equivalence point, but you may not know that in a question. So it's always the first thing you want to do when you're solving a titration problem is check where you're at so you can apply the appropriate strategy. Second, we need to calculate the moles of H3O remaining in the solution. Remember, we're going to add H3O plus, our HCl, but some of that is going to get neutralized. So we want to calculate the moles remaining in our solution. And once we've done that, we can convert the moles into a concentration. And then, of course, we can convert our concentration of hydronium into a pH. So here's the setup that we're going to be analyzing in this problem. We're going to say that we had a 30 ml sample of 0.200 molar ammonia in our flask. And here's the Kb for ammonia. And we're going to be adding a certain volume of 0.300 HCl, which will represent as hydronium, since that dissociates completely. So here's the problem we want to look at in this video. We want to calculate the pH of our solution after the addition of 35 milliliters of 0.300 molar HCl. Now, we went over those steps very briefly. Pause the video, work ahead, and see if you can solve the problem correctly. Give it a try, then watch the video and follow along and see if you did it correctly. Okay, so the first thing we need to do, we've added 35 milliliters of our acid. Let's see if that puts us before, at, or beyond the equivalence point. Okay. So we want to compare the moles of ammonia that we started with the moles of acid that we've added. That's going to tell us where we're at on our titration curve. So the moles of ammonia initial, we take our 30 mils, convert it to liters, and we multiply that times the molarity of ammonia, which is given in the problem. Be sure you've written that problem down so you can follow along. Our liters cancel, and we end up with 0.00600 moles of ammonia. That's what we started with. Now, how many moles of acid have we added? Well, we take our volume, 35 mils, into liters, and multiply it times the molarity. Our liters cancel, and we end up with, since we have a 0.3 molar HCl solution, we've added 0.0105 moles of acid. So let's compare these two. Obviously, the moles of acid is greater than the moles of base. So we've added more than enough moles of acid to neutralize all of that base that we started with. So we're past the equivalence point. We know that because our moles of base initial is less than the moles of acid added. Therefore, we're past or beyond the equivalence point. So be sure you can do this calculation before you begin any titration problem. So second, let's calculate the moles of H3O, H3O plus remaining, not total, but remaining in the solution. Remember, up to the equivalence point, every time we added 1 mole of hydronium or 1 mole of acid, it got neutralized because we had a mole of weak base there, up to the equivalence point. So we need to first, let's calculate the total moles of H3O plus added, which we already did just then. Then let's calculate the moles of NH3 initially present. Again, we just did that calculation. Then we want to subtract these two. Subtract the moles of ammonia from the moles of acid. Because remember, for every mole of ammonia that we had, it neutralized 1 of the moles of acid that we added. Okay, so let's calculate the moles of ammonia initial and the total moles of H3O plus added. Okay, again, we just did those calculations, so here they are again. So beyond the equivalence point, each mole of H3O plus added is neutralized by 1 of the moles of ammonia that we had present. Again, that stoichiometry is critical to this. So since we started with 0.006 moles of ammonia, that tells us that 0.006 moles of acid was neutralized. So let's calculate the moles of hydronium remaining, and we're just going to subtract the moles of H3O plus neutralized. You see that's just the moles of ammonia that we started with. We're subtracting that from the total moles of hydronium that we added. And so how much hydronium, how many moles of hydronium do we have remaining? Well, 0.00450 moles remaining. Now, in order to get a pH, we have to convert that into a concentration. So let's divide, of course, by the total volume. So what's our total volume? Well, of course, our total volume is going to be the volume that we started with. We started, remember, with 30 milliliters of ammonia, and we've added, our question said that we added 35 mils of acid. So we just have to convert those to liters, add them together, and divide the moles of H3O plus remaining by the total volume, 65 milliliters converted to liters, and we get a concentration now. Our concentration of hydronium is 0.0692 molar hydronium. Once we get that, it's an easy conversion to get that into a pH. We take the concentration and the negative log of that, and we get a very acidic pH, which is what we would expect. 1.160 is our pH. So beyond the equivalence point, we would expect that to be fairly acidic. So be sure you can recognize where you're at on the titration curve by calculating your moles and comparing them. And then beyond the equivalence point, be sure you can calculate the pH as we've done here.